Hi everyone, welcome back once again. Let's continue the part 3 in which we had been designing the shear links for our simply supported beam. Yet we are not done, and hopefully in the next video we should make it. As what we stated before, the assist VRDC, that is the capacity of my concrete without using any shear links, also called the stirrups, was itself incapable of resisting the applied shear force. And thus rebars in a form of shear links must be engaged, in order, of course, to avoid any sudden catastrophic shear failure near to the support. Now, for the sake of better understanding, before digging into the shear links design of our example, let's look first at what really happens as the applied shear force, the VED, exceeds the member shear resistance with no shear links or less are being employed. Basically, the shear force applied get increased, the concrete resistance, the VRDC, would hold no capability of resisting the applied shear force. This would lead to two possible shear failure scenarios. One is due to the diagonal tensile force, and two is due to the compression diagonal force, which results in concrete being crushed. Right, let's look at them one by one. The first one is simply avoided by providing the shear links. In this case, at least in our example, the vertical shear links. Shear links are obtained by working out the ratio, the ASW over S, which will define the diameter of my stirrups and its spacing. The VRDS will be then equated with the VED, and Z is just 0.9D. FYWD is the grade of steel used in the stirrups, which in this case, I'm going to take it as 500 megapascal, just as the one used in the flexure design. One term, though, remains unknown and must be figured out, otherwise the ratio will not be possibly calculated. That is the theta here. So what is the theta? Essentially, the theta is related to the second failure type. That is the diagonal compression failure. So how does it work? What you observe here in blue dotted lines are the concrete compression struts, and they exist normally in concrete, but since concrete happens to be good in compression, they are there to take care of the second failure type, but certainly that is up to certain limits. The concrete compression strut is said to have a maximum resistance, the VRD max, and it's given by the code as the following equation. B is the breadth, Z is the same as before, FCD is the compressive strength of my concrete, the grade I'm using, by its partial factor of safety. V is the strength reduction factor. We'll see what that is equal to later on when we solve for our example. Now there is the theta again, and to make it in simple words, theta is just related to the applied shear force, the VED. Now, the more the VED, or the bigger, or the more VED, the bigger the theta gets, and the less the VED, the less theta gets. So, fortunately, most of the cases concerning loads in a form of UDL, theta would be taken to be 22 degrees. So, increasing the VED would also mean an increment of the theta. 22 degrees happens to be just the fine angle for the concrete strut to resist the second type of failure. So if the theta is 22 degrees, then the VRD max is larger than the VED. Okay, this is what we are trying to get to. So what that piece of information tells me is that when I get back to assess my area of stirrups over its spacing, The previously unknown theta would now be known and is set to be 22 degrees. Now, most of you might be wondering, what if the theta happens to be more than 22 degrees? Well, if the theta is more than 22 degrees, that means the VED is way bigger to be resisted by the VRD max. But what actually happens in this case? Would I be required to put some kind of special rebars, or would I need to resize my member? Well, the simple answer is none of what I have just mentioned. First of all, the angle cannot go beyond 45 degrees. At least this is the limit of my code. So it lies between this range, 22 degrees up to 45 degrees. If though I find the angle to be more than 45 degrees, then I must use, either I use a greater grade of concrete, or I just get back and resize my member. Luckily, the theta ranges between 22 up to 45 degrees. In this case, the theta is more than 22 degrees because the VRD max is less than the VED. In this case, the theta would be calculating using this equation. The VRD max would be equated with the VED here, and the theta would be simply obtained by simple plugging of variables. Once the theta is obtained, we only need to return to this equation and insert the new theta that has been already calculated above. Now, how would the theta larger than 22 degrees affect my design? Well, the stirrups at this situation would be used more intensively, meaning that when the theta is larger than 22 degrees, the ratio gonna be more, and thus more of stirrups will be required. Simple as that. By contrast, if the theta is equal to 22 degrees, the ratio would result in a smaller number, making less need of stirrups. Alright, let me summarize all of this. Shear links must be provided in order to control two possible types of failure: when the shear capacity of my beam is less than the applied shear force, the VED. Depending on the VED, I might use less or more shear links. In the case of the VRD max is larger than the VED, then this just would result in some saving of stirrups, because the second type of failure is confirmed to be controlled by the concrete struts. However, in the case of a larger applied force, the theta would rise above 22 degrees, and thus it must be calculating using this equation. Then with the same procedure, the theta would be substituted into this equation, with the theta of course being more than 22 degrees, but also less than or equal 45 degrees. Alright, by covering all of this, we should be good to go and design the stirrups of our simply supported beam, which we would be doing hopefully in the next part.